Right. Question 15 on the light worksheet. So they're asking us to link. We'll come to this. We'll come to that. They're asking us to link the critical angle and the refractive index. So refractive index is n, and c equals right. Right, so we're going to link those. So sine c equals 1 over n. 1 mark, simple, right? Now what they've done is they're going to give you 3 marks, 5 significant figures, the critical angle they've given you. So what they're saying to you is sine 88.500, right? It's important because they've given it to that accuracy for a reason, right? Equals 1 over n. Step 1. Step 2, rearrange that. It's a bit right, so, and then finally you can write 1.0003. It's 0. Right, it's 1.00034 and so on. But they wanted to 5 significant figures. So can you see how important it is to know significant figures, standard form before you come into your science exam? And physics is known to sort of cause a lot of headache. Right. Diagram 2 shows a ray of light from the sun. So look, let's just go back to this. What you've got to do is you've got to be careful that you don't get put off by just looking at that. That looks scary. So they've just asked for a simple, this is a simple maths question really. Just rearranging, substituting and rearranging. Right, diagram 2 shows ray. So you've got this incoming ray. They've drawn this line, and what is that line called? It's called the normal. Okay. The refractive index of the atmosphere is greater than the refractive index of space. Complete the diagram by drawing the path of the ray of light through the atmosphere. Right. So they're saying the refractive index n here for space, and this is n for atmosphere. This is bigger than this. If that's the case, you're going to bend towards the normal. Right, where are we? Just learn this. If you're going from a high refractive index to a low refractive index, you bend the light towards the normal. So what's going to happen, instead of it going straight, what's going to happen, it's going to bend, right, let's just do this. It's going to bend towards, so this is the refractive index, angle of refraction, and this is the angle of incidence. This is the incident ray, this one here, and this is the refracted ray, this one here. Yeah, I don't know. let's not extend it past that, just leave it there. Right, okay. That's it, done. Right. Explain why the ray of light does not change direction, right? Because you can just simply write angle of incidence is 0, so angle of refraction must also be 0. There you go. So that's how you get your 2 marks. So there's the normal. The angle of incidence is 0 here because look, normally we see a ray coming in that way and this is the angle of incidence. But they've moved that way. So you've got this now. Okay, there you go. So now what we need to do is explain why the wavelength of the light reduces when it enters the atmosphere. Right. Let's get this. So the first thing that happens is the formula, speed equals f lambda. So f stands for frequency. Let's write it in words. Times wavelength lambda. Remember wavelength is from trough to trough, from there to there. That is wavelength lambda. Right. First of all, the formula is speed equals frequency times wavelength. The frequency is constant of the wave. The frequency does not change. So if the speed, since speed changes, right, as you go from one medium here to a different medium here, they've got different density, so speed's going to alter. Since speed changes, right, so remember we said speed is, let's not use v, let's not use speed, so we'll say speed is f lambda. Doing it again, get rid of u. No, we don't want that. Did I just do that? Right, let's have a look. Get rid of that. Let me move this back up. That's distracting me. There you go. So v equals, right, speed. Right, the frequency stays the same. So if the speed drops, wavelength must also drop. Okay, for this to be equal. I mean, that's how you can learn it. So since speed changes, decreases, the the wavelength must also decrease. Right, okay, that's that done. Right, suggest why. We're looking at this one here now. Suggest why the sun appears not to be circular. Right, this is where you get up here. This is where this diagram comes in. So what's going to happen is that's coming at a different angle. That's coming at a different angle, and so they're gonna diffract different amounts. They're gonna refract different amounts. So what's gonna happen is it's gonna hit your eye. So it's gonna end up looking slightly overly. So what we can do is let's get a nice color. So for this one, light from different parts of the sun refract different amounts. So the amount of refraction is larger. Is it one marker? Yeah, okay. So the amount of refraction is larger when the sun is close to the horizon. Okay, just leave it like that. Just that there is more than enough for an answer. Okay, let's try to squeeze this one in. Right. So this is low density. This is high density. Right, let's draw the normal in. Remember, normal is at 90 degrees. We don't need to draw that 90 degree in. And then you've got the same thing here. That's your normal. That line is called the normal. Right. Right, so you've got your incident ray. This here is the angle of incidence. Angle of incidence. Right, because it's going from low to high, it bends towards the normal. So this is the refracted angle. Now you've got to be careful on this side here, because this here is now the angle of incidence and this is the angle of refraction. And have you noticed this is bigger than this because it's going from high density to low density. I always get that wrong. So when you go from high to low, it bends away from the normal. When you're going from low to high, it bends towards the normal here. Okay, so we've got all that. Some of the light is reflected from the surface at point A. So what they're saying is the ray comes in, some of it is refracted and some of it is reflected. So these two angles have to be the same, these two. Right, we got that. Use a protractor to determine the angle of incidence and the angle of refraction at point A. So basically what they want you to do is, look, they want you to measure this angle. So you draw in the normal, this red line, and you measure this, and then you can measure, let's use that. Then you've got to measure this pink one, and that is R, and that is I. So if you printed this out, which paper is it? It's question 9, January 2021, paper 1. Right, so it's paper 1. So don't be afraid of it. Give it a go. Angle of incidence is, they've measured it as 60 degrees, and the angle of refraction is 31 degrees. Well, don't need that. They've given us that. Right, state the formula linking refractive index, angle of incidence, and angle of refraction. Oh, right, okay. So remember those two formulae. Sine C equals 1 over n. That there is a critical angle, and this is the refractive index. Now they want us to work out the other formula. So they're saying n is the refractive index, is the sine infrared. This is the angle of incidence. Angle of incidence, and this is the refractive angle of. So let me write it out for you. Just making stuff up as I'm going on. Angle of refraction. There you go. So what you need to do is you need to write this here. Right, calculate the refractive index. So we've got I and we've got R. So all we do is we go to the side, and we write n equals sine 60 over sine 31, and then n equals 1.68. Simple maths question, that is. Describe how a student could improve investigation to obtain a more reliable value of index. Right, okay. Right, the first thing you can do is repeat readings at each angle. So do a few angles actually at each angle. Right, so then find, no, what we'll do is we'll do it this way. Then remove anomalies and find average. Right. Then you vary each angle of incidence. Right. Vary the angle of incidence. So you've got a range of angles of incidence. And then work out the refractive index. Work out the refractive index work out the refractive index. So first of all, what you do is, right, before you do that, you need to plot the sine I and sine R graph. Then you work out the refractive index by finding the gradient. By finding the gradient of the graph. We've done this before, haven't we? So 1, 2, 3, 4. So let's go through that again. So you repeat the readings at each angle of incidence, right? You vary the angle of incidence. So what you do is then you measure the angle of refraction, right? So you've got that. Plot the graph sine I and sine R, and then what you do is work out the refractive index by working out the gradient from this graph. That could be better written in plot the sine I and sine R graph. The student replaces the red light with the blue light. Diagram 2 shows any ray of blue light directed at point A at the same angle of incidence as the previous ray of red light. Whoa. Okay. The dashed lines show the previous path, right? Okay. How many marks is that? 3 marks. Okay. The refractive index is higher than the refractive index for the light. So what's going to happen is, so because it's higher, what's going to happen is you're going to draw, can I get away with this now? Let's try this. I hope it's right. Oh yeah, that's all right. Oh God, did I just do that? Let's draw that one again. Oh, that's terrible. That. How did that happen? No, it's gonna go grid to grid. I'm afraid I can't get away with that, so I'm gonna have to. Ooh. What? You telling me you can't turn that in a straight line? No, my fault. Oh. Got that. That doesn't help, does it? Not very clever. Right, listen, I'm wasting time. I am wasting time. I need to stop wasting time. I've just drawn the two normals. They've said the refractive index for blue light is higher than the refractive index for red light. So the dotted line is the red light. So because it's higher, remember we said if it's higher, you bend the light towards the normal more. So what's going to happen is this light's going to go, oh my word, it's not going to do that, is it really? From here, it's going to bend that way. And then so you've got your new normal here. Oh. And then it's going to bend back out. So it's going to take this sort of path. Right, I've got to be a bit more accurate with this. It's gonna be it has to be parallel to the red light. So this is the blue light. Do you know I should have done it in blue, shouldn't I? That doesn't help, does it? This is. I understand how students feel. Now you're gonna say finally. Right, and then it's gonna draw a parallel line. There you go. Why did that happen for? Because I left that on. Right, okay. So this angle is going to be smaller, the angle of refraction, and these two here are parallel. Right, okay. Is that it? Oh, guess what? It's finally finished. Congratulations, Mr. Khan. Right, done. Long live light.